G'day guys, welcome back to In My Shed. I'm BC. This is going to be part 1 of my abrasive machining course. I still haven't found the software to put it into a proper course format, but I haven't started charging yet either, so you're getting value for money. Okay, a little bit of history. I've been selling industrial abrasives for 42 years and using it for many years beforehand. I did a specialist custom built abrasive specified course with Norton Abrasives back in the late 80s. There's a lot of very technical information, and when I hear people talk about a grinding rock or a grinding stone, I shudder. We haven't used natural abrasives for probably nearly a century. I'll give you a little bit of a rundown of what I know, a couple of little snippets of information that I very rarely see anyone talk about, and I think they're pretty important bits of information. It gives you a bit more of an insight into the usage of grinding wheels. Okay, first up, the main types of grain that we'll see used. Gone are the days of natural abrasive. In my working lifetime, I've only ever seen crocus cloth as an apprentice, and crocus is a flour and there's a natural grit in the flour and it's used for extreme polishing. It was a J-weight cloth, triple flexed, and it was stretched straight and then flexed over a blade in 2 different directions at 45 degrees, and it brought up a good finish, but it was a bloody slow process. Emery cloth, well, the emery grain was superseded before I came into industry. Aluminium oxide's been used for many years now, and that's about all I can think of. Sand or sandstone has been out of the picture for a long time. What we will see in industry, other than super abrasives, and this is what is the common garden variety product still. First one up is Alox. Alox is the trade name. It's aluminium oxide. It's created by filling an enormous room with alumina, that's aluminium ore, borax I think as a flux, and a few doping agents. They put carbon or graphite electrodes in both ends of it, and they apply 1,000,000 amps. This must cost them $100 an hour electricity cost. After about 2 days, the electric arc wakes it through into the middle, and it becomes an arc furnace, and from the middle out it fuses all the alumina and it creates aluminium oxide crystal. Now it's all virtually one giant fused crystal. It varies from the cream or white colour in the centre with Alox out to grey or black at the outside, and that varies the grade. The bit in the middle, the white and the cream, is very high quality, high purity, and able to grind up to Rockwell 62C, something like that. And then you come out to the brown and orange, then you get into the grey and then into the black, which is usually thrown away. It's all smashed up, still put into a sieve to get you your grit size, and the grit size, the 60, is still the number of grits per inch in the sieve. So we haven't got to metric yet with grinding wheels. Even the diameter is still 8 inch or 200 mil, but it's more like 8 inch. Okay, it's sieved, put out into whatever use they want. The good quality white Alox is used in tool room work, and also for the white no-fill paper that you use on painting cars or timber. And if ever you want just a small amount of abrasive grain of a particular grit, buy some aluminium oxide paper and burn it off. When you blow all the dust away, you're left with the abrasive grain and a bit of soot, etc., and you can make up a grit mop or whatever you want of a particular grain. It's usually almost an equal angle triangle, or isosceles triangle I think, and it's reasonably sharp. Comes to a point. It could vary in toughness depending on the grade, but it's a good all-round abrasive. Silicon carbide is made with silica, sand, with all the shite washed out of it, graphite for the carbon, once again 1,000,000 amps, and after it's fused you finish up with a very bright green in the middle, which is 39C, going out to a grey colour, which is regular C I think, and then out to the black that gets thrown in the bin. The 39C is a very pointed triangle. It's also a hell of a lot harder than aluminium oxide, and being pointy and hard makes it extremely sharp. So it's what you use for non-ferrous material, where you want to minimise the impingement into the material wherever possible, or for non-ferrous hard materials like tungsten carbide, etc. Now these particular wheels have been around for long before I started my time. The silicon carbide wasn't very common when I first started because it was only used on expensive exotic materials, mainly tungsten carbide or stellite, materials like Hastelloy W, which are really difficult to work. And then in the 80s it became a lot more prevalent, and in the late 80s I was specifying that for very unusual circumstances. I had a customer once who was doing a petrochem valve rebuild. They stellited the valve and they'd been at it with the cylinder grinder for about 3 or 4 days and hadn't taken a thou out of the bore, so I suggested a 39C wheel of that particular spec, which is still one of my favourites. And I had one of the partners on the phone, "This bloody wheel hasn't lasted a day and it cost us $200 more." And I said, "But Jim, how much work did it do on that day?" "It's done about as much work as you would have done in a month with the previous wheel." So it's soft, it has very high attrition rate and you have to be careful in your tolerances, but it cuts very, very well, and on some difficult stainless steels it's very, very good. Okay, the next one down, it's in common use, not so much in vitrified wheels, mainly in coated abrasives, is your cubic zirconia. That's a man-made product. As the name suggests, it's cubic in shape, it's as tough as hell, and it has a very unique ability in that when it starts to wear and it gets whacked, it can break between 4 and 7 times and form a new, almost square edge. So it's a self-regenerating abrasive, provided you work it hard enough. If you work it just lightly, it's going to glaze over and then you finish up with stuff all. Being quite a blocky grain, it needs a bit more swarf space, so if it's in a coated abrasive, like sanding discs, it's fabulous for the aluminium industry because they put it down in what's called an open coat. They spread the grain out over a fair bit more surface area, and that gives a lot of space for the swarf to gather, and it'll throw off into the wind and doesn't tend to load the abrasives as much. Now, in reinforced type wheels, you get a good mix. You can have a cubic zirconia, now there's new ceramic wheels, but we won't go into super abrasives, and you can have an aluminium oxide and cubic zirconia mix. The Alox is reasonably sharp and the cubic zirconia maintains the shape of the wheel. It prevents the wheel from being dressed back or roughed back very, very quickly. That's a pretty well run through on what type of grain we have. Now, bond type and quality. I remember back when I was very young, we actually did a bit of education on shellac bonded wheels. Bloody varnish for timber, and it was used then for very, very narrow cut-off wheels for doing the nibs for ink writing, the old bloody quill pen. It went out of favour quite often. In tool room work, you've got a straight resinoid bond, which is used mainly for tool room cut-off wheels, non-reinforced type, which are very thin, and it's also used in foundry work for big straight cup wheels and for plug wheels, most likely with silicon carbide abrasive for cast irons. The silicon carbide and silk carb Alox mix is very, very good there. Quality of the bond. There we come down to what material makes up the bond, and the higher the quality of the bond, the less of that bond that you have to use. And here's one of the first anomalies. A lot of people talk about 39C, and I forgot the bloody C, which is the grain type, silk carb. 60 is your grit number, H is your hardness, and then comes 8, which is structure. Now, structure is what they call the bond post to pore space ratio. Bloody hell, that's a mouthful. You can see all the little abrasive grains, and I'll zoom you in a little bit on this fantastic drawing later on. And between the bonds you have between the grains you have the bond post, the sticky bit between the grains, and in between the bond posts you have the pore space. And the pore space is where the swarf hides before you release it out into the world, and also where the cooling air or cooling solution takes place or takes hold and does its job. Now, in a real cheap and nasty, shitty Asian grinding wheel years ago, they had what I called 100% flooded bond. They used the cheapest bond that had very, very little strength, so there was no pore space, nowhere for the swarf to go, and you would sit there and grind and get something awful hot, and nothing would happen. They've since picked their act up quite a bit, and some of the Asian wheels are now almost up to the good quality specialty abrasives. We have a few other different grains, some specialty grains, and I better talk about those. One of the first I come across was a product called Hermeset by Hermes, and they used very, very small ceramic particles to form a sphere that was hollow. They then crushed the sphere and used the parts of the sphere to bond down to the abrasive paper or abrasive cloth, and the sphere would set up and become a cup-shaped, very, very hard abrasive, and it would wear the small particles away but maintain its shape, and had quite a good life. It was very, very aggressive and a really good product. Now you've got seeded gel from Norton, which is mainly used in tool room wheels, where it replaces aluminium oxide, and it's a whole lot of little grains that make one big grain, and then they crush that, and that has this resharpening or rebuilding ability. I've only used these late model composite materials, a very, very small amount, and they are bloody fantastic. In a flared cup wheel, I've tried the Norton high performance abrasive, and you can hardly even hear that thing cutting, and it just throws the material off, job done. Really, really good product. The structure, they can vary quite a bit. I think the lower the structure number, the harder the wheel, or the harder it acts, and I think 8 is pretty well as high as they go. And I'll show you a different twig on the structure. V is for vitrified, K is a modified vitrified bond, so the wheel is not dressed by the work as much. That was developed, I think, in the late 80s, early 90s, and you'll see on bench grinder wheels it'll be A60, probably MN, and quite often the structure was missed, but then it would be VK at the back end. The last two letters from that special wheel I talked about for the Stellite job, PL, or pour induced. Not used a lot nowadays, but it used to be a premium product. Green silicon carbide, when they mix up the batch to make the abrasive wheels, and I think the minimum quantity was 15 kilos that they would batch. So the smaller the wheel, the greater number of wheels you had to take. They mix in little pieces of wax, and they can be of whatever size they want, and as they fire the vitrified wheel in the kiln, the wax melts out and you're left with a porous wheel. And that is really good for a number of reasons. It can pick up coolant and take it with it, although you should really dry the wheel out before you start the machine first time of the day, or it can let a lot of air in and keep the job cool, and it also lets a lot of swarf in. And this is a very popular product for grinding brazed carbide lathe tools after you ground the supporting steel matrix away behind. And a couple of things about balancing these wheels. You see in this wheel there's a black arrow. When they dress this wheel, they put it up on a balancing machine and they find the heaviest point, and that's where they put the arrow, or it can't be a straight line. This is on wheels 150 diameter or larger. And when you place the wheel on the arbor, that arrow should be up, being the heaviest point. If there's a little bit of slop, the wheel will fall down, and that will help to balance the wheel on the machine. Give you a lot less to do on the benchtop balancing stand. Now, a more modern way of balancing, and I've only seen this on a couple of wheels because there has to be a fair whack out before it's used. They either vapor blast the side of the wheel to remove a little bit of grain, or they'll shock blast the side of the wheel to impinge a little bit of grain, and it looks like a pimple on the side of the wheel, either negative or positive, and that's where they shock blast them. Now, with all of these tool room or general purpose wheels, I advise not to dress the side of them unless they're a recessed one side wheel, even though I myself use the side of the wheel on drill grinding, etc. Because if the wheels are balanced by a little bob you might not see, and you dress it and you dress the balancing action out of it, then the wheel is virtually buggered. You have to throw it away or rebalance it in some fashion. Usage of the wheels. Aluminium oxide, all round good guy, especially for metalworking. Everything up to drill bits, fairly hard tools, not the extreme hard tools, but yeah, very good. It'll even grind cobalt, high-speed steel. It's cheap. One big problem I see in the usage of tool room wheels, especially on things like surface grinders or cylindrical grinders, tool and cutter grinders, people think a surface grinder can take a 10th hour deep cut and plough the bloody material off. Well, the action of an abrasive, it's a friction machining tool, and it rubs on the surface until the surface gets red hot, and then it tears a bit of material off the surface and flings it off in the form of a spark. That's not the abrasive grain you see shooting away, that's actually the workpiece. Now, if you try to take a couple of thou too many, what happens is you'll overheat the workpiece and glaze it, then it'll become very, very hot, and then it will shed the grain, because that's what the bond is designed to do. As the grain gets blunt, it's shed so that a new group of abrasive grains can come up and do the job. And if you exceed the mechanical strength that the wheel can absorb, the wheel will just physically fail. Now, I've seen that out on site when I was a young apprentice. An apprentice was given a star wheel dresser to go and dress all the wheels around the workshop, and I don't know if you've noticed, but the star wheel dresser has two little feet at the front, and nobody told him how to use it. They're no good on the late model bench grinders with the sheet metal work rests, but with the older grinders you would move the work rest back, hook the two legs over the back of it and lift the back of the dresser, and the star wheels would impinge onto the wheel and crush dress it. That was the name of the action. If you didn't do it like that, you could be like this poor fellow. He chipped a piece out of the side of the wheel and it nailed it down. So if you're using star wheel dressers, use them appropriately, please. Diamond dressers are very good for getting the wheels flat, and then I usually use a DS1 silicon carbide dressing stick, which is very good for just a quick hand dress. Silicon carbide wheels, once again, for non-ferrous materials. They can also be used on glass, some plastics and ceramics. Very, very good product. And balancing. That's about it in a nutshell. If you look after these wheels, you can get fantastic life out of them, and the best way to appreciate them is treat them like a multi-tooth milling cutter. These are a tooth cutting tool, and if you got your milling cutter head and put it on fast reverse across the top of the workpiece, it would dance around across the workpiece, and if the machine was rigid enough it would break something. So don't get your grinding wheel and have the work traversing underneath it backwards and forwards. You'll get nowhere except frustrated and a shithouse finish. The rule of thumb is start off with 1 to 1.5 thou if you're roughing, and half a thou to spark out if you're finishing. And if you're on a really rigid machine like a cylindrical grinder and you have a mistake, you can have a bloody bad accident. So please keep that in mind. I'll get behind the camera now and try and zoom you in a little bit. I'll show you the bit of a mud map here and show you the wheels. That's the silicon carbide wheel, and this one is an Alox. Very simple to differentiate them. That gives you a better look at my mud map on the bond post to pore space ratio. Very important to consider that. That's why you dress a wheel to get rid of all the bond in between the abrasive grains and let the grain have a go and do its work. And that's the spec from the 1980s. 39 should be a C between the 9 and the 60, H8 VKPL. That wheel there is a bench grinder wheel, not a wheel for a cylindrical grinder, etc. And I think it's an M grade. The bench grinder wheels are always a little bit harder to make up for the fettling and all the hard work that you give them. Now, if you like the information I'm putting out, I will keep going and try and form a reasonable course. Abrasives are not just them grinding things. That's a bit of an insult to a very scientific part of industry. They do a fabulous job, and they can do jobs you can't get done any other way. Okay, I'll finish gas bagging. Please like and subscribe if this is the first time on your channel. I've got lots of videos on tool and colour grinding, etc. Okay guys, have a good weekend.